A metal wire length 8 centimeters is heated at one end. The table above gives selected values of the temperature, T of x in degrees Celsius, and of the wire x centimeters from the heated end. The function t is decreasing and twice differentiable. Estimate t prime of 7, show the work that leads to your answers, indicate units of measure. So this is definitely a problem, unlike the problem before where we do want to indicate our units of measure, but nonetheless we're estimating the derivative with the table. That means rise over run. 7 would be between 6 and 8, right? So we'll label this x1 y1 x2 y2. So let's go ahead and estimate t prime of 7 is approximately, well, 55 minus 62 divided by 8 minus 6, right? And again, if we go ahead and do that, just doing some work, we get negative 7 divided by 2. What's our units? Well, delta rise over, delta y over delta x. So we start with this. This is the temperature, which is what? Degrees Celsius per, and what is our units on delta x? Well, it's centimeters. Centimeters per cm. All right, there we go. And we are in business. And if you want to, you could do degrees Celsius divided by cm, but nonetheless, always nice to be able to kind of write this out down here. All right, so there it is. That is part A, my friends. We are completing part A, ready to move on, trying to do these as quickly as possible, but also well, I put some explanations enough. So let's go to part B. Write an integral expression in terms of T of z for the average temperature of the wire. Estimate the average temperature of the wire using a trapezoid sum with 4 sub-intervals indicated by the data in the table. Okay. So we want to write an integral expression in terms of T of x for the average temperature of the wire. Now, as we've always gone through, anytime we want to find the average temperature, right? Well, we have to think to ourselves, what are we taking the average from? Well, the average is from 0, looking at the table values, 0 to 8 centimeters. So for this part, we're gonna get 1 over 8. That would be the average, right? The integral from 0 to 8, and we want the average temperature. Well, guess what? T of x is the temperature, so this is going to give me the average temperature of my function. So now we have this here. Now we want to estimate the average temperature using a trapezoid sum. So now that we have our integral, well, it's basically saying, hey, now go ahead and actually estimate it down. Now again, some of you are able to do this just by looking at the table. I personally, at this point, we just want to make sure I get full points on this. So even if it takes me an additional 1 minute to have to do this here, I'm okay with that. And it looks like it's descending from 193, 70, 62, and 50. So I'll put 100 up here, 93 right here, 70 here, 62 here, and 55 there. Very good. So 0, it's at 100. At 1, it's at 93. At 5, it's at 70. 6, it's at 62. And 8, it's at 55. Bam. There it is. So now we have that there. Now we want to draw, we want to do 4 trapezoid sums. So there's obviously, if you look on the graph, it makes sense that we're going to have 4 trapezoids, right? Well, here's your first trapezoid right there. Bam. Bam. It's that first trapezoid. We get our second trapezoid here, our third trapezoid there, and last but not least, our fourth trapezoid here, right? There it is. Good. Just like always, I like to write down, right? This width is 1, this width is 4, this width is 1, and that width is 2. Usually I like to put the length up here, but it's a trapezoid, so we'll do some work for that. So let's go ahead and begin. 1 over 8, 0 to 8, T of x dx is approximately equal to, all right, well, it's a trapezoid. Remember, trapezoids is still length times width, right? Our width is 1. Well, how about our length? Well, we notice they have different lengths, and that's okay. How do we get that difference in length? Well, we add them and divide by 2, right? That'll take the average or the difference of those 2 lengths and give you the length of that trapezoid. So, nonetheless, we get 100 plus 93 divided by 2 multiplied by 1. Which is your width, right? There's the width right there. We took into account the 2 lengths plus, and we'll do the same thing, which is 93 plus 70 divided by 2. Oops, hold on real quick. 93 plus 70 divided by 2 multiplied by 4 plus 70 plus 62 divided by 2 multiplied by 1. Right? I'm just kind of going through doing this part here was the next part. Then we did this length up here with this length right there. That was 62. Now we'll do 62, which is this length plus 55. So plus 62 plus 55 divided by 2 times 2. Very good, right? And again, some of you like to put your brackets around here. And don't forget, I did this on purpose, right? I did this on purpose to indicate to you guys how easy it is to make a mistake. Right now, if I wrote this on the test, I would get 0 points. Do you know why? Well, don't forget the 1/8 in front. That's why I left some space there, right? And I'm put it in these brackets with the 1/8 in front. Very important, my friends, that if you're doing the average, that has to be in your approximation. So I left it out just to show you how easy it is to accidentally avoid it. But keep in mind, this should always be in front, right? So if you wanted to, I ideally would have started it then with as 1/8, and then I'll go ahead and fill out the rest here, right? So again, I just showed you just to show you how naturally it might feel, and hopefully that'll be something you can remember, not to forget if that's to come up for you. Before we go and finish this problem off, we get 1/8 from 0 to 8 t of x. dx is approximately 1/8. Try to do some mental math if you can, right? Well, these 2's cancel out here, right? Because you're dividing by 2, multiplying by 2, gone here, right? 4 divided by 2 is 2, so this will be multiplying by 2. This is multiplying by 1, right? So I don't really need to worry about that there, right? So it might be good to try to do some mental math. Now, keep in mind, one of the things you definitely want to do is don't write on over this on the AP exam. Keep it as is perfectly, but just keep a mental note of it, right? So 100 plus 93 is 193 divided by 2 is 96.5 plus 93 plus 70 is 163 times 2 is 326 plus 70 plus 62 divided by 2 is 66 plus 62 plus 55, which is 117. Very good. We get 1/8. Boom. And let's go ahead and begin to add the rest of these down, right? So that we can get the best approximation possible. 96.5 plus 326 plus 66 plus 117 divided by 8. So we're going to get 605.5, right? Divided by 8, which is 75.6875 degrees Celsius, right? And again, if you needed to, remember you could just leave it 605.5 divided by 8, and then we got our temperature there. So I just kind of went through that very quickly. Again, that's just doing some mental math as we kind of go along. And now we know, right, this is the average temperature change from t equals 0 to t equals 8. So that gives us our approximation. That's worth 3 points. The problem up above was worth 1 point. And we're doing pretty good, right, in terms of where we are pacing wise. Let's go ahead and go to the next part, part C. Find this here and indicate units of measure. Explain the meaning of this, right? Well, all right, let's just kind of begin. I know this may seem kind of challenging here, but let's just begin with what we know. We're taking the antiderivative of t prime. So that's just going to get me the original, right? You're given the derivative, right? I guess if you want to, we could write PVA. You're given the derivative, or which would be here, and the antiderivative gets us back to our original. So this is the derivative. Taking the anti, we get back to our original from 0 to 8. And that just means we just plug it in. T of 0. This is t of 8. Well, that's just the table values up here. So t of 8 is 55 minus 100, which is negative 45 degrees Celsius, right? Just double checking to make sure it wasn't Fahrenheit. I want to make sure I'm pretty good with my units. There it is. Explain the meaning of this. Well, what is the meaning of this? Well, my friends, you know, we got back to temperature, right? When we took the antiderivative of this, we're back to temperature, and we're evaluating. We plugged in 8 and 0, so we're evaluating it right here. We'll do this evaluation. So what is that telling us? Well, what was this problem about? This problem was about a metal wire that is heated on one end, and the table above gives us selected values of the temperature. So what can we conclude about this metal wire, the temperature of this metal wire? Well, from T equals 0 to T equals 8, the temperature dropped, right? The temperature dropped by 45 degrees Celsius. So we can say this T prime of x dx means the temperature drops by 45 degrees Celsius from the heated end of the wire to the other end. There it is. So it means the temperature dropped by 45 degrees from the heated end of the wire to the other end of the wire, right? And that's pretty much what we have right here, right? It's heated at one end. It gives us the temperature of the wire x centimeters from the heated end, right? So it's telling us how much the temperature has dropped of this metal wire, right? So there you go, my friends. So that is the explanation there. Let's go to part D. Are the data in the table consistent with the assertion that T double prime of x is greater than 0 in the interval here? Well, this is going to involve the mean value theorem. And this can be pretty tough, right? So if you're ready for part D, that's something that I'll give you some resources on in an answer key separately. But for now, I just want to go over the problems that I really want you to focus on being able to get right if they showed up, and the ones that I think you will have more success with. So this, right? I will pass out an answer key for you to be able to make sense of this, and then ask me if you need help. But for the purposes of these videos, I just want to make sure that you get that confidence on every single kind of question and the parts that are most important. All right, good. Take it.